Welcome back. In this video, we're going to talk about where valuable multivariable functions might show up in your life. Remember, in the last videos, we talked about that in this class, we study multivariable differentiation, also known as the process of taking multivariable derivatives. This is the forward problem of multivariable calculus in the sense that we apply the derivative, aka what we know as the gradient operator, to a known multivariable function. And in this case, I'm going to call the input variables m and b instead of x and y. So this is what's going to be known as a valuable multivariable function. Notice, I'm not saying that this is given because in this video we're going to see we actually have to construct this. Mathematicians love to ignore this fact. We like to pretend that math is just given, it falls from the sky. But you're going to see, in order to have a useful function, we actually have to do a lot of work. So anyways, in this class we apply the gradient operator to a known multivariable function. And then the whole point of M1C is to produce the partial derivatives of this function. And there are two of them in this case because there are two input variables. If there were three input variables, there would be three partial derivatives. So these were the partial derivatives of the original multivariable function. So the whole idea of this class is to give you this theory, to allow you to calculate this, and then also how to use these to your benefit. All of this necessitates that we as users understand what the hell this function is and why we would ever use it. One source of valuable, extremely valuable in fact, multivariable functions comes from curve fitting. Which is another way to say trying to construct a best fit function to describe collected data. Let's take a look at an example. To show how this might arise. All right, we're going to take a look at an example that has some relevance to today's political conversations, which is to talk about the number of CO2 particles observed at the Mauna Loa Observatory in Hawaii. This is a very, very famous data set known as the Keeling curve. You can Google search that if you're very excited about life and math. Here I'm going to take a subset of 14 data points. Over here, this is the point number. So here the first data point was taken in 1980. So T sub 1 is 0 years into this data collection because it's the first year, aka the 0th year of the data set. And then the number of CO2 parts per million observed average for that year in Mauna Loa was 338.7. So the second data point in this set was taken in 1982. So T sub 2 is equal to 2 because it's 2 years after the start of this experiment. In that year, the parts per million CO2 in the atmosphere observed at this observatory was average 341.1 CO2 parts per million. And you can see there's 14 different data points here. I'm going to go ahead and save you some work. You could put this into Excel and graph it. And eventually what would happen is you would get a graph that looks just like this. So down here you see this is the year, which is not the variable t. It's just the year of the data point. And then up here is CO2 parts per million. And what you see is these dots are the individual dots from that data. So in particular, this first dot here, we're going to call that one T1, Y1. And we saw that that was actually corresponding to T1 was 0 at 1980, and Y1 was 338.7 parts per million. Here, the second one, we had this as T2, and you can rewind this video to confirm that I'm not lying to you. I would encourage you to do that. Okay, the second year was 1982, which is 2 years after the start. And then the amount of CO2 in the atmosphere of this observatory average was 341.1. Notice that T is equal to the year minus 1980, because 1980 is the start. So when the first year was 1980, 1980 minus 1980 is 0. 1982 minus 1980 is 2, etc., etc. And we can continue down here. The third one, if you look back at this, of course, this is going to be 1984, which is 4, and then this was 344.4, etc., etc. And it goes all the way down. In this case, we had 14 different data points that we took here. And the most amazing thing, this is actually real data. I did not make this up. I got this from Stewart Calculus, actually. And let's see, this was going to be, I guess this is 16, I suppose, because I think it's 2006. I guess it's 26, I'm sorry. And then this would be 381.9. Okay, so here we have this set of data, and that's the actual dots. The drawn line here represents the idea that there seems to be a trend here. And in particular, we could ask a pre-calculus student, do you see any function that you might use to describe this data? And that pre-calculus student might say, well, it kind of looks like it's growing like a line, growing linearly. Okay. Well, that is a very deep statement. The sad thing is that this data set actually grows exponentially, which is quite scary. Meaning to say the number of parts per million has grown exponentially over the last few centuries. But locally, it does look like a linear thing, which means that we might assume when we graph this data on an axis, it seems the data approximately follows a linear model. Which is to say, oh God, a linear model, of course. Which is to say, y equals, well, we don't know the slope. This is an unknown variable. T is the independent variable, the number of years after 1980. And then in a linear model, we also need to have a y-intercept. This is unknown in the general linear model, but it seems to be that it follows this. Where unknown slope m and unknown y-intercept b need to be chosen to best fit, and this is where things get really exciting, don't you think? The collected data. This is where we can do something clever. Okay, so the whole idea is, let's go back and look at this data. We've studied the world around us. We collected data, which is often quite expensive. We have 14 data points that fall not exactly on a line. They're not collinear. But the trend in the data seems to be linear growth over time. We assume that if this is true, we should be able to find some curve, some mathematical model, which we're going to call y equals mx plus b, and we need to find the m and the b. Of course, it's mt plus b because t is the number of years after 1980 in this model. So we want to choose m and b to get this, what seems to be best fit curve, right? Okay. So let's think about what is going on here. So for the ith data point, and in this case we said that I ran between 1 and 14 because there were 14 different data points, we see t sub I, y sub I is our collected data, which we can graph. Okay, so here we have this graph. These are not the t and y axis at all. These are just, meaning to say the scale on this graph is not accurate. I'm literally just using this graphical image to represent an idea. Okay, so the idea was that any particular data point might not go through the exact modeled line that I wanted, right? Because there's error in the way that we collect data, depending on how I choose my M and B, the collected output value might not be the modeled output value. And why don't we do this? Why don't we say, let's define the ith modeled output as y sub I hat, and this is going to be equal to, of course, a function of whichever m and b I choose. Do you see the multivariable function there? Whoa, that's crazy, isn't it? Plus b. Right? So the output value of the linear model at the input point would be y sub I hat, whereas the actual collected observed data is going to be y sub I. So this is the modeled point from the line of best fit. And then this is the observed data from the scientific study. Okay? Now, the fact that there's a difference here means that we might be able to quantify it. We could actually define, let's define the error between the model data here and the actual data as, and this error is dependent on the data number, so we'll call that E sub I. This is going to be the actual data minus the modeled output. Well, of course, we know exactly how to calculate that based on the fact that the output there we're claiming should be a function of whatever slope I choose to model and whatever y-intercept, which means each error, depending on the slope and the intercept, the individual error in the ith component is actually a multivariable function. Times t sub I, and then maybe we go minus b. It doesn't really matter to me. It's algebra at this point. Okay. Well, there are a total of 14 different data points. Each of these is the individual error. The question that we have to ask for now is to say, well, now that we have the individual error, how do we use each individual error together to be able to create a function that allows us to figure out which is the best m and b? To answer this question, please join me in the next video.